We saw that in general, surfactants want to get their hydrophobic tail out of water, or if we're working in a non-aqueous system, what we can say is they want to get their lyophobic part out of the solvent. One way they can do this, we saw, was to form an aggregate. The aggregate that you're probably most familiar with is a spherical micelle. This drawing is a little bit misleading in that it implies that all the chains are straight and pointing towards the center. This is basically a liquid phase, so the chains are completely disorganized and pointing in all different directions. That's only one morphology you can form. You can also imagine slicing a sphere in half and then separating it by a big distance, and then in the middle putting a cylinder, and that's what we're showing here as a cylindrical portion of a rod micelle. So this could be, since this is a cylinder, we could extend this out as long as we wanted, and then we'd cap it with half of a spherical micelle on either end. And by that way we get the chains out of the water and have the head groups in the water. Okay, so we could imagine forming a rod micelle. We could also imagine forming a bilayer. You're familiar with bilayers from your biology courses, and so you know that a bilayer is simply taking surfactant molecules and putting them in a layer 1 molecule thick with the head groups facing the water. So if we had a bilayer, that would mean that we had water here and water down here, and then we have this oil-soluble layer in between. So these are 3 different types of aggregates we could have. Which of these aggregates we get would depend upon the solvent that we had and also the surfactant number. We can see that spherical micelles have less space for the tail and more for the head, a little bit less so for rod micelles, and here we have roughly equal space for the tail and for the head group. So that implies there's a different surfactant number that's ideal for each of these morphologies. You should derive what exact surfactant number is ideal for each of these geometries as an exercise. Note that I've drawn these all, or shown these all, for systems where we have polar head groups in water. If we were to place any of these surfactants in an organic solvent, we can imagine forming inverse spherical micelles, where the chains would be pointing out and the head groups pointing in. We could have an inverse rod micelle, with the tails pointing out and the head groups pointing in. And of course, we could have an inverse bilayer, where the head groups are together and the chains are pointing out. If the concentration of surfactant is high enough, these aggregates can pack into lyotropic liquid crystals. Lyo just meaning solvent. So these are liquid crystals that change their structure based on the composition of the solvent. Okay, so here's a schematic that I've taken from a Wikipedia article on lyotropic liquid crystals that shows we've got temperature on this axis and increasing concentration of surfactant on the x-axis. And we can see that as we start to go into higher concentrations of surfactant, the aggregates pack into different structures. So at a very low concentration, we just have micelles and they're just floating around in a disorganized isotropic system. But if we go to a higher concentration, we get this phase, which is a cubic, basically this is a cubic close-packed liquid crystal of surfactant molecules. So it's still liquid, the molecules are still free to move within each micelle, and water diffuses freely between them, but they're packed into a close-packed array. That's the cubic phase. And here, if we go to higher concentrations of surfactant, we can get this hexagonal phase. Now notice in this case, we have rod micelles, and the rod micelles are packed into a hexagonal packing. And you can mimic this yourself. If you just grab a bunch of pencils and hold them together, they'll naturally packed into an hexagonal array. So you can see there's a hexagon here, and then there's another rod in the center of the hexagon. If we keep increasing the concentration, we can get this phase. And this is a really neat phase because if we look at this, it's different from the other two we've looked at. So in this phase, the continuous phase is water, and the oil is packed into each micelle as a different oily compartment. In the hexagonal phase, we have tubes of oil, but they're not, that oily phase is not continuous with In other words, if you were an oil molecule, you could diffuse inside each micelle, but you couldn't get from one rod to another. But the water is continuous. In this phase, both the oil compartment and the water are continuous. So this is called the cubic bicontinuous. Because in this phase, we put an oil molecule into the surfactant, it could diffuse along this tube to all the other tubes. They're all one connected network. And of course, the water phase is also continuous. So there's two separate interconnected networks in the cubic bicontinuous phase. And going further to even higher concentration, we get the lamellar phase. And you can see there's a lipid bilayer here and a separate liquid bilayer, and they can stack. So it's a stacked phase. This green over here is when we go to really high concentration, we exceed the solubility of the surfactant. And here we've gone to such high concentration of surfactant that it falls out of solution. So this is just solid surfactant. Two things we should say about this diagram. First, not every surfactant will have all of these phases. And second, these do not exhaust the possibilities for lyotropic liquid crystals. For instance, if we were to have an organic solvent that's nonpolar, we can imagine an inverted cubic phase where all of these micelles are flipped inside out with their tails sticking out into the nonpolar solvent. We can have an inverted hexagonal phase, an inverted cubic bicontinuous phase, and an inverse lamellar phase where instead of having water between the layers, you would have oil between the layers and the head groups would be touching.